It's time for us to get going now. Actually, we're starting a minute late. Sorry about that. Is Megan here? Okay, thank you. Didn't see you. And is Utah here? No. Okay. So starting out, we're going to be talking about equilibrium and simple machines today. Just for clarification, we have a test next Tuesday. The material that we're doing today won't be on the test. It's the stuff that we finished with last period. Question, Gabriel. Man. They clearly can't hear me over there at Southwestern. I don't know why. I'm going to lower their volume there because they have it on, assuming I'm not talking or something. I don't know. So I'm going to get started, and hopefully they'll figure out why they're not hearing. We did test it and make sure that sound is going out of our system on Google Hangouts. So, I had the question here. The picture of the gentleman working on installing the air conditioner. You saw the caption, why women live longer than men. Obviously a joke. But if you look at that, I have a simple question. Is this an equilibrium situation?
It's not on the screen.
Yeah, but the picture.
It's not yet there.
It's, I'm like, are you guys crazy? I'm pretty sure they don't hear me, so if they can't hear me, what are they going to do?
Oh, okay,
yeah. But this time it's not our fault. We can verify that. Okay, so now you can see the picture perfectly in focus. Are they in equilibrium?
Yes.
How do you know they're in equilibrium?
Because he's not falling.
Okay, because he's not falling. Being a little more specific, the acceleration is 0 and the rotational acceleration, which we give a symbol of alpha, is 0. I know. I mean, there's nothing else I can do, right? We verified that they're getting there. Okay, so we have the angular acceleration is 0. That means the rate of rotation is not changing. Now, we haven't learned that angular acceleration term yet, so that's one of the things we're going to learn about today is what causes angular rotation. We still won't have the angular acceleration term, but we'll have torques, which are the things that cause angular acceleration. So just something of curiosity that has to do with equilibrium. The Leaning Tower of PISA, is that in equilibrium? To any reasonable measurement, the answer is yes, because its acceleration is virtually 0. It has changed over time. You could see the difference in the tilts from when it was first built. Started off nice and stable. Started vertical, and then they had a period where they did no construction for about 100 years, and it tipped quite a bit. And then they said, well, we should build more. And they went for another about 100 years, tipped some more. They built it taller because, hasn't fallen over yet. Why not build it taller? They have done a lot of work recently to buttress it, to give it a firmer foundation, and actually to tilt it back some. Because, of course, you don't want to fall over. But going back to, I think it was 2 lectures ago when I was using Colton as an example of trying to push me over, what situation do we really need for this tower to be in equilibrium? Okay, something else pushing against it could help to keep it from falling over, but just freestanding. What's the situation? I'm looking for the situation involving the center of mass to keep it in equilibrium. The center of mass needs to be between the edges of the base, so over the base. And so if we look at the Leaning Tower of Pisa, the center of mass is going to be somewhere right around there. Right? It's not this line going from the top. That's not going from the center of mass. And so if you just drop a vertical from that, that's as close as I can get to vertical, it's well within the base. So it's still going to be in equilibrium. It's not going to fall over. Now, if it tipped over far enough that the center of mass was above that point, I'd be all she wrote. Right? Then it would tip over. Yeah, you could say, you could have people pile up over here or something, try to hold it down, but generally that would be a loss of stability. This is not the only such thing in the world. San Francisco has their Millennium Tower, a tower that was completed, I think, around 2010. At the time when it was completed, before people moved in, it was noted that it was sinking. But somehow the city inspector said, that's okay. So some people are, alleging that there was some bribery going on there. They didn't tell any of the people who paid millions of dollars for their apartments that it was sinking. And it wasn't until the BART terminal that's being built next door did some studies that they discovered, yes, they have known for a long time, just haven't told anyone that it's sinking. So it sunk a total of 16 inches and it says 2 inches of tilt, which I didn't verify if that means the top has moved 2 inches or the base has moved 2 inches, but it's starting to tilt. And of course, residents are really upset about this. They're suing, saying that their property values went from $10 million for an apartment to zero, although I saw another article that said a standard apartment in the complex, the price plummeted from 3.8 million to 3.6 million because of this. I would still be happy to have a $3.6 million property, but it's a concern. So if you're an engineer, one of the things you have to worry about is, and we talked about this last class period, the wise man builds his house upon the rock. The foolish man builds his house upon the sand. This is built, the Millennium Tower in San Francisco is built on sand. Now they put a bunch of pilings in. You drive those pilings deep enough in the sand, you put a lot of force, it's considered stable. Something you guys may not even remember. Do you guys remember the Loma Prieta earthquake? No, of course not. I forgot your age. I was like, it was my brother's senior year in high school. I was in graduate school. Yeah. It was in, 1991-ish or something? Yeah. I think it was 1990. Anyway, in San Francisco, the Marina District had liquefaction. That is, it's built on fill, and that fill started swooshing like it was liquid. And that Millennium Tower is built on a similar situation. If they have an earthquake, it could all swash out. And so I would tend to say they weren't wise in their construction. The official Bay Area Rapid Transit, the people building terminal next door, they say the problem is that they should have drilled down 200 feet to get into bedrock. The people who built the Millennium Tower says it's because the Bay Area Rapid Transit people pumped water out of the sand, and that caused the sand to settle. So everybody's blaming everyone else because that's the way we work in America, right? Like with the sound problem, not my fault, right? All right, so let's talk about torque, a new thing. I love introducing torque because I always talk about my dad. Back when I was like 6 or 7 years old, my dad, my Uncle Jack, not the famous Jack Webb, just like I'm not the famous Richard Webb. If you ever go to Hollywood and see the star for Richard Webb, obviously not me. So my dad and my Uncle Jack are talking about a car. And my dad says, man, that engine's got a lot of torque. And I was like, Daddy, what's torque? My dad thinks for a minute and he says, well, it's kind of the amount of twist that it has. And little 6 or 7 year old me was still cynical enough that I just said to myself, okay, Dad doesn't know what torque is. He's making stuff up. And I went on. But I remembered it because I was very curious about this word torque. And it turns out, as I studied physics, I found out my dad wasn't so wrong after all. That the amount of twist is actually a really accurate description for what torque is. Torque is the rotational equivalent to a force. A force, anything that pushes or pulls. And Newton's second law tells us that forces will cause accelerations. Well, a torque is a force that's going to cause a rotational motion. So it's got a force causing a twist. And there is a rotational equivalent to Newton's second law that says the angular acceleration, the rate at which something rotates, or changes its rotation, not rotates, but changes its rotational rate, is proportional to that torque. So we need to understand what torque is, because our conditions of equilibrium, some of the forces is zero and some of the torques is zero. So torque. Torque has an equation of R cross F. The radius crossed with force. Now, any normal person who hasn't had algebra is going to say, hasn't had linear algebra, let me be a little more specific, is going to say that means radius times force. But that's wrong, because they're vectors. How do you multiply directions? What's direction east times direction east? That's meaningless. So the cross product is something special, just like the dot product was a kind of multiplication between vectors that was multiplying the parallel parts. The cross product is multiplying the perpendicular parts. My stand is falling. So if I have a radius and a force, I take the perpendicular parts and multiply them together. So if you take, just as a simple example, just like when we had work, we have a radius like this. Now this is a radius, not a distance of motion. So it's a different thing. And I have a force that's like this. If I'm going to multiply the perpendicular parts, I need to, for instance, break the force or the radius into its perpendicular part, the component perpendicular. So you basically need to choose which one do I want to take my angle from. I can choose either one, so I will have error and choose. Which one should I choose my angle from?
Are you asking like which?
Either F, R, or F. Yeah.
From F.
Okay, so from F. So I'm going to break R into its perpendicular component to F. So if I'm going to find the angle from F, I'll put that angle in here. There's my angle theta between R and F. And then I want to say, well, R is made up of a piece that is parallel and a piece that's perpendicular. So here's a perpendicular direction. Here's a parallel direction. And it's only this R perpendicular that is going to contribute torque. The R parallel, it's not motion, so it's not going to do work. It's just not going to contribute in our calculation. So if R is which side of my right triangle is R here? Instead of saying if it is, which side is R? It's the hypotenuse. And R perpendicular is opposite. So that means R perpendicular must be equal to R times sine of the angle, because sine is opposite over hypotenuse. Or to put it, I should have put it this way first. And so the perpendicular part is R sine theta. Yes, I can hear your sound just fine. It's not going to be very well. You could turn it on, that we'll get some feedback. And yeah, actually, go ahead and do that and say, "Can you hear from this computer?" So I'm going to keep talking. He'll talk, do his own thing. I'm going to go with yes because I heard the feed. Well, actually, no, because I'm hearing I heard it, but it doesn't look like they did. I did hear the feedback. Okay, moving on. So if I want to find the torque, it's the perpendicular parts. So the torque, I put parallel lines on each side. That means the magnitude. That torque magnitude is the force times the radius perpendicular. So force times R sine of the angle between the two. Now remember when we did the work, it was a dot product, the amount's parallel, and it was force times distance times cosine of the angle between the two. Yeah, mute it because we're getting feedback. Up. So that's where this equation here comes in, the torque magnitude. And so if I use torque, that's a Greek letter tau for torque. If I use torque without the vector sign, that just means the magnitude, is the radius times the force times the sine theta. Now I need to define the radius before I move on because you can get really confused on this. Radius is the distance from the pivot point to where the force acts. So as an example, if I take this mass, I hold it out, the pivot point is going to be my shoulder. And so the radius will be the vector going from my shoulder out to where the force is. So the radius is pointing that direction. So right now, if I hold it out here, my radius is out. What direction is the force? Down. What's the angle between the two? 9 degrees. So that means sine of 9 degrees is 1, and my torque is going to be this radius times that force. So that's what the torque is, what the R is. The R is sometimes called the lever arm. It's always the distance that goes from where the pivot point is to where the force acts. So it's important to be able to remember that so you can figure out how to calculate a torque. Torques are always calculated about a point. So you always identify this is my pivot point. The torque about this point from this force is R cross F. Now there's a second thing about torque. It has a direction. The dot products, they're called a scalar product sometimes because there's no direction involved. But a torque has direction, so it's sometimes called a vector product because you get a vector for your answer. And the way to get that direction, we use our right hand. So the first thing, and I'd like everybody to actually pull out the old right hand and try to do this with me. The first thing you do is you take your right hand, extend your index finger straight in front of it, so it's straight, no bends. Put your middle finger so it's at 90 degrees to that, and your thumb so it's at 9 degrees. Each one of your fingers then should be perpendicular to the others. Don't get them backward. Don't try to do like this. I've got to use the hand so it doesn't look like a bad gesture. This would be wrong, okay? You need to have the index going straight and the middle finger pointing out in the normal direction from the palm, if you will. Now, the way we use this with the cross product is you always have the answer is going to be the direction of your thumb. The first vector is the direction of your index finger, and the second vector is the direction of your middle finger. So if you take the example of me holding the mass out here. Now, this is actually not super easy, so we want to go kind of quick. What direction do you point your index finger? And actually do it. Point your index finger the direction of the radius, because radius was the first thing in the cross product. And then orient your hand so your middle finger can point the direction of the force. And that's the force applied by the mass. Okay, most people are with me, but if you are not, the radius, index finger should be pointing that direction. Middle finger should be pointing down. This is my left hand, so it's going to be opposite. But just those two fingers should look like this. Then your thumb points the direction of the torque. So what direction is the torque created about my shoulder due to this mass? That direction. If I moved it over here, you have to point your index finger the opposite direction. And remember, yes, you can rotate all over the place. When you're doing a test problem with this, you can rotate your paper. Now your thumb is pointing toward me. That's called the right hand rule. We use it a lot in physics, but this is the first time you've seen it. Now we can use the right hand rule in some other ways. That torque will cause a rotation. And you could answer real quickly. When I had it out here, you said the torque was going away from me. What direction would this rotate if I stopped holding it up? If I just let my shoulder relax? It'd go like this, right? So that would be, would it be clockwise or counterclockwise? Okay, so it'd be counterclockwise if the torque is going toward you. We define coming out of the thing as the positive direction if we're just going to use positives and negatives. And so counterclockwise is the positive direction for rotation. Clockwise is the negative direction. That's why when we measure angles, we pretty much exclusively measure our angles in the counterclockwise direction, because that's the direction we consider the positive direction for an angle. We have another version of the right-hand rule to get that straight. If you wrap your fingers the way it rotates of your right hand, then your thumb points the direction that we assign to that rotation. So if you look at the second hand of the clock, you wrap your fingers the way it's rotating, and thumb points in, right? Because it's rotating in a clockwise direction. Thumb points in, so we say that's a negative rotation because it's going in. When you put a screw in, what's the way you remember the direction to put the screw in? Righty-tighty, lefty-loosey. All that is a statement of the right-hand rule, because we make right-hand threads on our screws and bolts and whatnot for the most part. So I don't sit there and say righty-tighty, lefty-loosey. I wrap my right hand and say, I want it to go that direction, so I've got to turn it this way. That's how I do it because, hey, I'm a physicist. There are some threads that are left-hand threads. Some of you probably worked like in chemistry with gases, and you have some gases that are nice and fun to play with, like helium, and some gases that are not at all fun to play with, like krypton. I used a krypton fluoride. Actually, krypton's not the problem, it's the fluoride. Krypton fluoride laser when I was in graduate school, vaporizing materials with a 248 nanometer laser beam that's made from an excited dimer of krypton fluoride. Well, that fluoride, the tank, you don't want that fluoride to spill out or leak out of the tank. And one of the things that can be really bad is if you put a regulator on that has normal rubber gaskets, the fluorine gas will just eat those away. And then you leak out that fluorine gas. And when I read the material safety data sheet on fluorine gas, I decided I did not want to deal with that. So to make it so you don't put the wrong regulator on the bottle, they use left-hand threads on, gases of a certain type. And they'll use different gauges for different types of gas. So that basically, if your regulator fits, it should be safe to use. So that's where we have left-hand threads sometimes, and there are other places. So left-hand threads, well, if you use your left hand, just think about the clock. If I use my left hand, did the same thing, wrap my fingers the direction its second hand is rotating, my thumb would point the opposite direction. That's why you have to use the right hand, because they're mirror images. In organic chemistry, you have the same thing when you're talking about chirality. So torque, R cross F, comes into play a lot of different places. So we have an example here of showing a person holding, of course, a physics book with these muscles. You have a biceps muscle, two heads, that's pulling up, making a force up, and then you have a bone-on-bone force that's pushing down. You have the weight of the arm pulling down and the weight of that book pulling down. If you're going to sit there and hold it, for equilibrium, you have to have two conditions true. The sum of the forces has to be zero. So I can take these and say, okay, the force of the bicep up has to equal the sum of the other three that are down, so that they add up to a total of zero. But that wouldn't be enough for me to solve much of anything. But I have another rule: the sum of the torques has to be zero. And a very good question to ask is the sum of the torques about what point? Here's a really cool thing. It doesn't matter. You can choose any point to sum the torques about. The sum of the torques is going to have to be zero. So that means you can choose the point to sum your torques to best fit your knowns and what you're looking for. So for instance, let us say that I gave you the mass of the arm, and I gave you the mass of the book, and I asked you to find the force of the biceps muscle. How many forces do I not know if I only gave you those two masses? And of course, I have to have all of the distances for this. So I give you those three distances and the two masses. How many forces do you not know? Two. Of those two, I only asked for one, the biceps. So I don't know the force of the bone on bone, called FE for force elbow here. And furthermore, I don't care about it. Now, I might have a second part that says, and what's the force of the elbow? But for starters, I didn't care about it. I can solve this with just one equation using the torques condition, because the sum of the torques has to be 0. And so I will choose a pivot point. So this lower picture is just showing the same thing laid out for us. So if I choose a pivot point appropriately or judiciously, apparently we're practicing shooting. If I choose it judiciously, I can make it so the force of the elbow does not matter. Now remember, torque is R cross F, or the force times radius perpendicular. In this case, all my forces are vertical, and I'm going to choose a point to sum that's on the axis where all the forces act, or on that line, so that my angles will all be 90 degrees. That'll make life easy, right? If I chose a point to sum my torques like up here, then I would have my radii are going, excellent. Radii are going like this and like that and like that. Well, that would make my life more difficult, generally speaking. So I'm going to choose to sum my torques about something that is on this axis where they're all acting, and I want to have no torque from the elbow. Well, since torque is R perpendicular times force, the force isn't 0, so how can I make the torque from the elbow 0? I'm going to write these all down without putting signs. I put them without signs because there's another question to ask. But how can I make that first one 0 if we know the force of the elbow is not 0? By setting what to 0? Okay, the radius for the elbow. If I choose the place I'm going to sum so the radius for the elbow is 0, then that force won't make any torque. It won't cause any rotation. And so that's what I'm going to do. I'm going to sum my torques about this point. Now I need to put in my signs before I actually do the calculations. So signs. Do you remember the rules for what's a positive versus a negative torque? Mahala says yes. No, that's good. It's good to say yes. I'm not going to pick on her. I'm just pleased that she was responding. So basic rules, right-hand rule, if it's clockwise, is that a positive or negative torque? Negative. If it's counterclockwise, positive or negative? Positive. So we look at these. The force of the bicep, would that make it rotate in a clockwise or counterclockwise direction? Counter. So is that positive or negative?
Positive.
Okay. So that's a positive. What about, I called it C for center of mass. Here it's A for arm. Is that going to make it clockwise or counterclockwise? Clockwise. So is that positive or negative? Negative. And then the book, clockwise or counterclockwise? It's going to be clockwise because the force is like this. And of course, you can use your R cross. I'm doing it from my way. For you, it's going to be R cross F. It's going in, it's negative, it's clockwise. So I got my signs there by using the right-hand rule, whether it's by looking at the rotation it would cause or if it's just doing the strict right-hand rule, R cross F. Now I'll put in the numbers. 0 times force of the elbow, because I'm summing the torques about that pivot point, plus the radius for the biceps was 4 centimeters. And the force of the bicep, I do not know, minus the radius for the center of mass, which was 16 centimeters, times the force of the center of mass, which I know is 2.5 kilograms times G. Actually, I wanted that. And then finally, for the last one was 38 centimeters. And 4.0 kilograms. Now, if you look at this, the discerning mind says, I have centimeters times kilograms, meters per second squared, or centimeters times newtons. That's kind of mixed units, right? But when I solve this for force B, I'm going to divide everything by centimeters, right? And so the centimeters are going to cancel out. As long as I have, unless it's my final answer, as long as I have the same units for all of the distances and the same units for all the forces, it doesn't matter if they're mixed. So you could do centimeters times pounds if you wanted. Nobody talks about a torque in units of centimeter pounds. They either use foot times pound or Newton times meter. And remember, a Newton meter is a joule, but when you're talking about torque, you never ever use joule. It's always a Newton times a meter. So I'm just going to leave the units as they are. And so then I have to take these other two and multiply them through. Do I have a brave soul who will do the math for me?
First one's 392.
This one's 1489.6.
80.
Okay, so there I've done the calculation through. I want to solve for F3. So I'll have F3 is equal to, adding those two together, you get what? 1882. Divided by 4.0 centimeters. So 470.5 newtons. How many significant digits do I have in this answer? Okay, just like on the test, this is a little complicated. You have to look at these and say, okay, these were multiplied, but I didn't know FB, so that was just 2 digits for the 4.0 and then unknown for FB. This here, the multiplication, the smallest number of significant digits was 2, so my answer has 2 significant digits. So that was significant to that level. The 1490, again, was only 2 significant, so that was significant to that level. When I add those two together, it's going to be the greater of my least significant digit, so it's only good to the 100th digit. So this was only good to that level. Divided, it was actually 2 significant digits divided by 2 significant digits, which makes it real clear that this only had 2 significant digits. So 470 newtons is my correct answer to correct significant digits. Now, this is a very typical type of equilibrium problem. I'm going to go through a few more things, and then I'm going to work I guess I'm going to end the lecture without talking about simple machines because I'm going to work a bigger problem. Any questions on this process of using the equilibrium condition? This one, the torque equilibrium condition. Let me ask you one more question then. After I've done this and I found force 3, if I wanted to find force 3, force of the bicep is what that was. If I wanted to find the force of the elbow joint, how do I find that? So now I want to find this. How do I find it now that I found the force of the bicep muscle?
Set a different point about which to calculate the torque.
Okay, one option would be choose another point. Any point would work, right? There are some more convenient than others. Jordan.
Well, F9 equals 0, correct? So
An easier method is to use force net as 0 now. Because in this case, I know the other 3 forces, and just adding things up is easier than multiplying by distance and adding them up. And you don't have to worry about the directions as much. You just say, well, FB minus FE minus F, what I called C, minus FB equals 0. And you end up with right away. You end up with that. And so you just have to put your numbers in. So once you get the first one, the second one turned out to be much easier. And the first one was easier than it could have been because I judiciously chose the point where I was going to sum the torques about. If I had chosen to sum my torques about, let's say here, I would have had two unknowns in my torque equation. And I would have had to use another equation. I could have used this equation that I just did from Newton's second law, or I could have summed the torques about another location. Well, who wants to do the extra work? So not on the test coming up next week, but the one following that, you're going to have some kind of question on equilibrium and think about where's the best place to sum the torques to make my life the easiest. Okay, our first clicker question. They still haven't figured out the sound over there, but they can participate in this clicker question nonetheless because it shows up on their phones. So suppose you hold a weight out to the left side of your body, like, yeah. What direction is the torque created about your shoulder by that weight? Paris was first. Just saying. I really do feel bad about them over there not hearing us, but as long as we're sending sound, what can I do? Yeah.
When you say about like to the shoulder,
It's the torque about this location, right? Because you could have calculated the torque about that celestial sphere due to this mass. It would be kind of meaningless, but you could have done it. Okay, I'll give it about another 10 seconds. Using my fingers so the people over there know I'm counting down. So let's see, 10, 9, 8, 7. Okay. So what we got were 1, 11, 4, 5, 18, 3, and 8. So this is definitely a situation where you would do well to talk to the people around you. Now, the people over there at Southwestern you guys still don't hear me, right? Oh, you do hear me now? Oh, excellent. Okay. Well, now that they're involved, I'll turn the sound up so I can hear them if they... Okay, so we have a lot of varying opinions. So discuss among yourselves and see if you can come to some conclusions about the direction of a torque. And as I said, it's direction just like hold it out here with my left hand.
So it's going down the if you're holding it with your right hand and going like this, clockwise is there. So this one, right now, 5. So this is okay, so the force is going down. So if I hold it out, the force is going down. So that's for the now, what's the
if you hold the head and you're like push the same answer.
I mean, therefore, opposite direction.
Okay, go ahead and answer the question again now that you have discussed it with your neighbors. I saw some people doing some good legitimate explanation there, so hopefully we'll have better answers. Okay, give it about another 10 seconds to answer, and then I'll close it up. Okay. So we had 0, 0, 0, 0, 44, 1, 1.
That's a big change.
That's a big change. So Aaron, explain why. Okay, which answer did you get?
I did E.
Okay. There's a pretty good chance that you had chosen that. Explain why you chose E.
So I did the right hand rule, and it started out with it like this, and so it's your left arm, so the radius has your index finger pointing to the left, and then your force is downward, so your middle finger starts to go down, and so your thumb points inward.
Perfect. Now, I'm sure the people at Southwest couldn't hear your answer, so I'm going to repeat it. But she just looked at the radius. The radius is going from your shoulder to your left side. So you take your right hand, put your index finger in the direction of the radius. The force is down, so make your middle finger so it points down. Your thumb points to your rear side. Hence, the correct answer was to your rear side. This is a case where the discussion really worked well. And I saw some students explain it very nicely. That's makes the teacher happy. Okay, now another clicker question. Suppose you hold a weight to the left side of your body, your left arm straight. What arm angle produces the highest torque? So we're not asking about direction now. We're saying A is like this, B is like this. Okay, I gotta stand over here so you can see B. C is like this. D is, okay, more like that. D is like this. E is like this. And then F is like this. And G like that.
So if it's right at the horizontal, then yeah, so
Might wonder why I looked through them. Because the people at Southwestern weren't able to hear the entire lecture, I'm making sure I'm not asking them a question and putting somebody at a significant disadvantage. Okay, give it another couple seconds and we'll stop the. Okay, we had 11, 0, 26, 16, 0, 1. Now, we did not have a large group, but I'm still going to go straight to having somebody answer because I at least want to start the problem and I only have 5 minutes left. So, Gila, which one did you choose? Okay, why did you choose A?
because the sign of A
Okay.
compared to
Okay, now that's the wrong answer, but I understand your reasoning. What Gila said was that I have this A is a 90-degree angle, I guess, from horizontal. And so she took from that, 9 degrees, sine 9 degrees is 1. But you were taking the angle between the wrong things. What direction was the force pointing? The force was pointing downward. And so I need to take the angle between this direction and the arm's direction. So to get 90 degrees, C is the one that's going to be a right angle. And so that means C is the one that's going to have torque is equal to RF sine theta equals RF times 1. So that's going to be the biggest one. One of your homework problems, that's basically all there is to it. It asks you which one gives you the biggest torque, and it just varies the radius. They all have the same force magnitude, and varies the angle. Okay, so the correct answer was C, because it's perpendicular with all of the radii being the same arm length. Oh, yes, I forgot the cheater bar. Well, I won't talk about the cheater bar because then I won't have time to look at the problem. Here is a typical equilibrium problem. This is actually one of your homework problems. The complexity of this is bigger than the complexity of anything we've done so far, right? Because that's always the way it is with the homework. In class, we give you the simple cases. The homework will give you something a little more complex for you to apply the simple case knowledge to. On the test, we go back to more simple cases usually. Not always, obviously. So let's look at how you would approach this, or how you're going to approach this, because this is due at 6:55 p.m. on Friday. So notice it's problem number 3 even. Suppose an 880 kilogram, your mass will vary, car is on the bridge in the figure with its center of mass halfway between the hinges and the cable attachment. The bridge is supported by the cable and hinges only. The mass of the bridge is 2,500 kilograms. I have a picture, but the picture's not complete. It's missing one of the forces. So we need to put that force in. Which force is it missing? The force of gravity on the car. So I've got to put, here's my car. And so I have force, I'm just going to call it force of gravity car here. This one here I'm going to call force of gravity for the bridge. And then I'm going to call this the force of tension. And this one here I'm going to call the force of the hinge. Right? I don't like a naked F. To me, that's like, I don't know which force it is. And I don't like using T and W. So I put my labels like that. So I've added the additional force. I've got my labels with labels that I can use. Now I'm ready to work. So the first question you have to ask, if this question comes up on the test, you're not going to have the context of saying, here's an equilibrium problem. You have to look at it and determine what's going on here. Is this the problem that I should use Newton's second law for? Is it a problem I should use the work energy relation for? Is it a problem I should use conservation of momentum for? You have to go through all of those ideas. Most of them you probably can dismiss out of hand. But you have to go through and decide what ideas are pertinent. And so since we're doing equilibrium, it's got to be equilibrium problem. So it's an equilibrium problem. So sum of the force vectors equals 0, and sum of the torque vectors equals 0. How many forces do I not know? I don't know the force of the hinge and the force of the tension. I know the masses and I know acceleration of gravity, so I know the two weight forces, but I don't know those two. So I have two unknowns. What am I looking for? First is the tension in the cable. So I'm just going to focus on that. If I'm looking for the tension in the cable and I don't know the force of the hinge or the force of the tension, where's the best place to sum my torques?
The force of the hinge, right at that point.
Okay, the best place is going to be to sum them where the force of the hinge acts. And so that's what I'm going to do, sum the torques about the hinge. And so then I go through the process. I'm going to have 0 for the radius going from that point to where the force of the hinge is. Now let's look at the next force. Let's just go out in order. The next force is the force of gravity of the bridge, and that force is going downward. So what direction is that? Is that positive or negative torque? Okay. Fingers out, fingers down, points right into the screen. I'm doing it for mine. Okay. If you look up here, fingers out for the radius, fingers down for the force. Thumb goes in, so it's negative. So I have minus 1.5 meters times, and I'm just going to save time, put force gravity of the bridge. The next one is the car. Is that going to be a positive or negative torque? Minus distance there. Notice this is 7.5 going from the center of gravity to the end. So the total length is 9. Half of 9 is 4.5 meters. Don't make a mistake there when you're doing the problem. 4.5 meters times the force of gravity of the car. And then finally, the distance out to the last one, is that positive or negative from the tension? Positive. That distance is the entire 9.0 meters. And I'm going to have the force of tension, but I also have to have, because it's not a right angle, sine of the angle between the force of tension and the radius. What's that angle? 40 degrees. And what is the sum of the torques equal? Now I have an equation where I know everything in it except for the force of the tension. So I can solve force tension. Right now, this looked a lot more complicated than the one with the hand, but it's actually exactly the same. It looked more complicated because our directions weren't all vertical. And then for the second one, find the force in newtons exerted by the hinges on the bridge. Because it's not vertical, you're going to have to sum the forces in the x. Anytime you say x, you better define x and y equals 0, and sum of the force in the y direction equals 0. And then use the Pythagorean theorem to combine them to find the magnitude. Or sum the torques about any place that's not the hinge. So for instance, you could sum the torques about the far end. But you don't know the angle either, and so that's going to be hard. So it's easier to do it this way because you don't know the angle. All right, we're done for the day. I'm glad you guys got the sound going there eventually at Southwestern, and I will see you on Friday.